We survived the first test, it seems. So we're now going into some new material. Today we're gonna focus on moments, which I'm sure you've gotten in physics 3A, right?
No.
Torques? Do they call them torques in physics 3A? Yeah, moment arm. I said moment. Yeah, like there. Yeah. Oh, thank you. You've heard of moments? Is that what they call them? What do they call them in physics? Sorry? They call them torques? Yeah, you get a torque wrench, you don't get a moment wrench. Yeah, so so that is what we are looking at today. Slideshow? Oh, no, it's just this thing. What is it, this thing? Slideshow. Yeah, AKA torque. And it's a measure of a tendency of a force to cause a rotation about a body, about an axis. So in this case, the wrench is providing a moment about the z-axis for the bolt, right? It's trying to make the bolt spin about the z-axis. That's what the wrench is actually doing. And there's a force and a distance involved, and the moment is the product of those two. The magnitude of the moment is the magnitude of the force times perpendicular distance between the force and the axis. So this is a scalar equation. And today we're just doing scalar moments. These are actually going to, you'll see, they're actually going to be in 3 dimensions. They're actually better described by vectors, but today we're going to just use scalars. So this is a magnitude of moment about 0.0. This is the magnitude of a force. And this is the perpendicular distance. So the trick here, and the reason why vector formulations are a little bit easier is because you don't have to worry about that. Perpendicular distance from F to O. And more precisely, it's from the line of F. The line of action of F. F extending as a line infinitely in both directions. The closest approach that line comes to the axis of rotation, that's what D is. It's the shortest distance between a point and a line. Can you say the radius? It's not appropriate to say radius because a radius implies circle or arc. Yeah, it's a moment arm. Although, you know, we're going to use R for the position. There's a position vector. It's going to be a position vector in 3D, so there'll be R. But R doesn't mean radius; it means position. And the axis of rotation is perpendicular to directions of F and D, which is what the cross product is going to do for us when we work with vectors. But we're just not worrying about that right now. We're just doing scalar. Not all forces created. If you use the wrench in this way, would you be able to loosen the bolt? No, there's no twisting force at all. You're just pulling the bolt. You're going to break something, and it's not going to actually unloosen it, right? And that creates a tendency for a translation, but not a rotation about 0.0. What about this way? Is that going to cause a rotation about the z-axis? No, it's going to try to make it rotate, but not about the z-axis, right? It'll try to make it rotate about maybe the x-axis. But that's usually not what we want to do with bolts. Right. The sense of MO is, vector is given by the thumb of the right hand. So if the fingers are curling around in the rotation that the force is trying to make the whatever object is at O spin, then the thumb will be pointing in the direction of the vector formulation of the moment. But again, we're just talking about scalars. So in 2D, though, we're considering a counterclockwise rotation as positive because that's when the thumb is pointing right at us, right? If we're in 2D and your fingers are curling around in the direction of rotation, your thumb is pointing at you. We call that a positive. We're just going to call that a positive moment. You don't have to go with that, but remember when we said, like, when we do like the sum of the fx's, it's a good idea to say, you know, what you're calling your reference direction or what you're calling your positive reference direction. In the same way, when we do the sum of the moments, we can use something like this, indicating that counterclockwise is considered positive. And this is basically implied unless you specify otherwise, but it's kind of helpful to kind of put that down there to kind of make sure you don't forget. There's this notion of the sense of the moment, right? Is it positive or is it negative? And this kind of confuses people initially, so listen up. I'm going to tell you how you do this. It's actually not that hard. It's actually very easy. What you do is we're going to find the sense of the moment about O here. And what I want you to do is I want you to visualize that instead of seeing this whole thing at point O, you have like a water wheel, you know, like with all those veins going around it. And the arrow of the force is sort of the flow of some water that's going near the water wheel. And when the water wheel kind of intersects with that flow of the force, which way is the water wheel going to turn? In that first one, it's going to turn clockwise, right? You all see that? It's a real easy visualization, right? It's going to turn clockwise. And do we call that positive or negative? We call that negative. So the sense of that moment is going to be negative because it's making it spin clockwise, right? Does that make sense? Karen? Question, Karen? Okay. I see your eyes, you know. So some of you in back, you're like, I can't see your expression. I just see these eyes looking. The whole back row is kind of like that, except for Aziz, Victor. But that's a good analogy, right? It's a good heuristic. If you put a water wheel right here, which way is the water wheel going to spin with this force going up like that? Counterclockwise, right? So it's going to be a rotation this way. This is going to be a rotation this way. So we're going to call that negative. This is going to be considered positive. And what about this one here? Let's see, this is odd shape, right? Forget about that odd shape. Put a water wheel right at the origin where we're trying to think about it. Which way is the water wheel going to turn? It's going to turn this way, right? Can you see it? Yeah, put the water wheel at the axis of rotation. And which way is that going to spin? That's the sense of the moment, right? Real easy. Right? That's what I do. The magnitude of the moment is the product of the and of course, F doesn't actually have to cause any axial rotation. That's why we don't use a radius, right? Nothing's actually moving. This is statics. It's creating a tendency to rotate, but you know, hopefully nothing does rotate. And with a 100 Newton force pointing down with a 2-meter distance from O, you know, MO equals F times D. And you can write, you know, MO equals, well, this is perpendicular, isn't it? This distance here is perpendicular to the distance right from here to there. Do you agree? That's a perpendicular line there. And so this is our D, right? So F times D is going to be 100 newtons times 2 meters, which is going to be 200 Newton meters. And the sense of that rotation is going to be clockwise or counterclockwise? Clockwise. So therefore, we could say that that's minus 200 Newton meters. Right? And Again, you can think of a vector formulation if you care to. MO vector is going to be, minus 200 Newton meters in the k direction, right? It's going, in this case, if your fingers are going in the rotation, the sense of rotation of F, sort of trying to cause a rotation this way, your thumb's going to be pointing into the spring. And so we would call that minus in the minus k direction if this is X and Z is coming at us, right? So that's why we do that. Another case. In this case, we have a larger d, right? So MO now is still the same force, but what if we increase the moment arm? What do we get? Well, we get a larger torque, a larger moment. It becomes minus 500 Newton meters. All right. So it's a bigger moment, right? And with a large enough lever, you can move the moon, right? Who said that? Was it a Greek scientist or was it Laplace or somebody? Was it a Greek? Apocryphal? Okay. Hey, may I have somebody joining us? Should I pause and see who it is? Did Archimedes say that? Did you look it up? Archimedes, what an amazing person that person was. Where am I here? Here is my, we have a visitor. That was the first bell, but why can't I see? Oh, here it is. Connie, hey, Connie, hey. Can you hear us okay?
Yes.
Not hearing you. It does say your speakers, your microphone's going though. Well, it's nice if we can hear you. I don't know why we're not hearing you, but maybe we can look at that later because I want to continue with the lecture.
Okay.
Did she say something? Oh, you're coming out of the projector. That's actually even more fun. You're like this disembodied voice. You could chat too, but I often don't check those while I'm in PowerPoint mode, so I won't really see those. There's this chat thing here. You can check that out.
Okay, sounds good.
Great. My goal is to have a class where nobody's actually present in the classroom. They're all just watching online. Then I could do my lecture from home. But what happens if the force is not oriented at right angles to the distance, there, right? So you have this 5 meter thing, but is that a right angle between the force and the point O? It's not, right? So again, MO is F times D, but it has to be the perpendicular distance between the force and the point there. And so what you could do, this is called the principle of transmissibility. You can actually extrapolate the force along its direction as far as you need to until you find the line, the closest approach between the line of F and the point. And that is the D you have to find, because that makes a right angle. In this case, since we have a 30-degree angle here, this is 30 degrees, this is going to be 60 degrees, and you can use your applied trig skills. You can say, well, this distance here is 5 meters, right? So what's D according to trig? 5 meters is the hypotenuse. What's D? Well, let's have a formula for it. Yeah, it's 5 times the sine of 30 degrees, right? Which is 2.5 meters. So that's 2.5 meters. So then MO is 100 newtons times 2.5 meters, which is 250 Newton meters. Okay, questions? Now, for Connie or anybody else who might be wanting to watch the lecture online, it is possible for you to get the slide, the handout. If you have a printer at home, you can do that by going to the lecture, and then this link here is the handout. So if you're at home and you have a printer, you can print that out and you can sort of follow along the same way we're doing it in class. Okay. So let's do some more examples here, right? Determine the moment for each of these problems, right? You want to just try them real fast? These are all pretty good because the forces are all, it's easy to find that perpendicular distance because the forces are all sort of right at, the horizontal or vertical forces, making it pretty easy to solve. So just crank those through. I'm going to give you like 2 minutes. And if you don't want to calculate it all out, there's some, trig in there. You don't necessarily have to calculate. Just write the equation or the formula for it. That's fine too. Keep track of whether it's positive or negative as well. Although they're giving you a little hint with those blue arrows. Right, so what's the first one? The first one is? Yeah, it's going to be 60 pounds times the moment arm, which is 1 times the sine of 45 degrees. And that's because this is 1 foot, this bend here, instead of 45-degree angle, and so the actual distance is 1 times the sine of 45 degrees. And it's going counterclockwise, so that's considered positive. The next one is it's going to be 7 times 4, 3. Yep, because that's 4 minus 1. That's the important distance, how far that force is from that point of rotation. And so it's 21 kilonewton meters. And it is also going that way, which we consider positive. The next one's a little more complicated. In this case, it's 40 times, the moment arm here is going to be what? 4 plus 2 times the cosine of 30. Dylan is saying that's root 3. That's root 3 over 2 times 2. Yep. And it's going clockwise, which we're considering negative. And the last one, pretty easy, just 50 times 3/4. Meters, right? So pretty easy, just find the distance, find the force. But of course, these are actually easy problems because the forces are all oriented horizontally or vertically. When the forces are not at a horizontal or vertical angle, then it gets a little tricky to find those moment arms. So we're going to use a tool that's going to make it easier for us to do that. Isn't that a Led Zeppelin album? Someone Google that. I think it is. I'll play it at the end of the class. I think it's, no? I think it is. Anyway, distraction. So for coplanar forces, the resultant moment about a point equals the sum of the individual moments caused by each of the forces. So if you have multiple forces acting on a body, you can add up the moments of each of those forces, taken separately, add them together, and that will be the resultant moment, just like when you could do the resultant force, right? So that's pretty nice. The principle of moment says if you want to get all those moments added up, you take and just sum all the forces times all the moment arms together, right? So M10 is going to be the moment of force 1 about point O is going to be F1 times D1, its moment arm, which is going to be 50 times 2. And that is going to be, it's going to be clockwise. I think they're all clockwise. And that's going to make it minus 100 Newton meters, right? So that is why that arrow, meaning, the minus sign, not the equal sign. Clockwise rotation is why we're putting a minus sign in front of that. What about M20? That's going to be F2 times D2. It's going to be 30 times 5. It's going to be minus 150 Newton meters. And M30, well, that's going to be, we already sort of looked at that. That's going to be F3 times D3. But again, D3 is that distance here, which is 2.5 to this one already. So that's going to be 100 times 2.5 minus 250 Newton meters. So the net moment is the resultant moment about O is going to be minus 500 Newton meters. Or you can write 500 Newton meters with a clockwise arrow after it. So that's the principle of moments, right? What does it say? The resultant moment is the sum of all the moments taken separately, added together, right? Principle of moments. And the nice thing is we can use the principle of moments when we have diagonal forces, because without the principle of moments, we have to maybe do some really fancy trig or geometry to find that D, right? The moment arm for this problem is not very easy to find directly, because what you have to do is you got to extend F right along its line of action, and you got to find the closest distance that line comes to point O, which is somewhere over here. Trust me, you don't want to do this, right? This is not fun to actually solve random geometry trig problems to find the line, the closest approach, right? So the hard way to solve the next is, look, let's take this force and let's break it down into two sections. Why do I show? Oh yeah, I didn't want to actually do this, so this is the hard way. Actually, let me just show this to you. This is the hard way. You don't have to write this down. You're never going to have to do it this way. But just to kind of show you how painful it is, one way you would sort of need to find this distance L, which is sort of becomes the hypotenuse of this triangle with D in it, right? So that's going to be the square root of 5 squared plus 2 squared, square root of 29. Phi is this angle here, arctangent of 2/5, 21.8. Then you can find theta. Yikes, okay, pretty painful to do all this stuff. Are we sure we're going to get that right every time? Probably not. So here's the easy way. The easy way says, let's go ahead and break that force into two forces. We're going to resolve that force. Remember, resolving a force into an Fx component and an Fy component that taken together. So why am I putting Fx on the vertical component? Why aren't anybody asking any questions about that? Okay, we'll call that F2. And we can have another force here called F1. F1 and F2, right? F1 and F2 added together equals F, right? We're resolving that force into two components. So the resultant moment is going to equal the moment from F1 plus the moment from F2 about 0.0. And the nice thing is it's easy. we just have to take F1 times D1 plus F2 times D2. And the respective D is easy to find because those forces are vertically and horizontally aligned. Because we can draw these, right? We can extend F1 all the way over to the left side here. And we can find this distance D1, which is just the height right here of that thing on the right there. That's our D1. And we can extend F2 all the way down, and it's going to basically tell us that D2 is this distance right here. Did they teach you this in physics? They did, right? Okay. Yeah, so it's not that new. It's very useful, right? So F1 is, we're going to have to use some trig to find F1, right? But that's pretty easy. F1 is going to be what? What's F1? Someone besides Dylan. Scott, what's F1? Hundred cosine 30, which is 86.6 newtons. F2, what's F2? You're right, 100 sine 30, and which is going to be 50. Now, those are the magnitudes, okay? We're actually, yeah, F2 is negative, so we could put a negative there. But when you do the principle of moments to solve these things, the best way is not to get hung up on the signs of those things. It's weird, because normally you have to really worry about signs. In this case, you want to worry about what's the sense of the rotation that each of these forces is doing. And then the sign will come from the water wheel analysis of the rotation that that force wants to do around that thing. So you can just basically forget about the signs of the forces, focus on the magnitudes and the distances, do your products, and then after you do your products, then figure out whether it's the water wheel is going to be spinning clockwise or counterclockwise for each of those components. You see what I'm saying? So, our D1 is going to be 2 meters, and our D2 is going to be 5 meters. So our MO is going to be the product of F1 times D1, and leave space because you might have to add a minus sign here. Let's do F1 first. It's going to be 86.6 newtons times 2 meters. And the other one, so that's basically, yeah, that's this F1, this horizontal force times 2. And the other one's going to be 50 times 5, right? Now looking at each one of these things, if you put a water wheel here at the origin and it's intersecting this F1 force going across the top here, which way is the water wheel going to spin? Clockwise, that's called negative, so we put a minus sign in there. F2, same deal, that stream F2 gushing down, hits the edge of the water wheel there, which way the water wheel spins? Clockwise, so they're both negative. It doesn't always have to be that way. But when we add this together, we get that it's 423 Newton meters, and it is clockwise. So, or you could say that it's minus 400 feet. It is, no, it's a 2, I don't know why it got so nasty there. It's just, oh, it's just 2 meters. I don't know why. What happened there? It does look like a 24, but it should be just 2 meters. Not funny. Okay, because, what about a situation where they're different? Well, what if the force was actually going this way, right? What if we had a force going this way? Actually, let's just do it maybe somewhere else so it doesn't mess up your thing here. Let's do it on this one. Suppose we had a force going this way. The components are now going to be like this and like this, or this one might be F1, this one might be F2. And the sense of the moment provided by F1, is that positive or negative? Yeah, F1 is causing a rotation this way, but F2 is causing a rotation in the other way, right? Now they actually are kind of working against each other. They're going to be sort of canceling stuff out a little bit. And it kind of makes sense, right? Because when you extend this force, it actually comes very close to 0.0, right? So it should have a relatively small moment because the moment arm is actually pretty small because it's pointing kind of close to the axis of rotation, right? You see what I'm saying? And it's possible that you could have a force pointing right at that thing, right? In which case, the moment provided by the horizontal part is going to exactly balance the moment provided by the vertical part. So they add up to 0. Just a conceptual thing. Okay, we're skipping over that because you don't really need that in your notes. And that's basically simple moments. Any questions before we move on to the next topic? We're kind of covering 2 things at the same time, which, because we only have 1 lecture this week, we're going to do problem session tomorrow. And really good problem session to be at because moments can be very confusing. So good way to kind of work that through. Any questions on regular moments before we go on to couples? Did they cover couples in physics? No couples? Okay. A couple is when you have 2 parallel forces with equal magnitudes and opposite directions separated by some distance between them. And those generate a pure rotation. There's no translation at all involved in a couple, right? Because if you add those forces together, you're just going to get 0. The sum of the forces is 0. But they're offset from each other. They're not actually acting along a common line. And because they're offset, you end up getting like a rotational effect, right? They actually want to cause a spin. And you know that makes sense if you're trying to really turn something. It kind of helps to have, on both sides to do that as opposed to just one. So, and in this case, the moment of a couple is just, again, which seems a little weird, it's just the product of the force times now it's the distance between those 2 forces. It's the magnitude of the force times the separation distance, the parallel perpendicular separation distance of those 2 forces. Seems like it should be something different, but we're going to see why that is in a second. That's the moment of a couple. So they're a little strange. And we're going to look at 3 situations here on the next slide where we have 2 20-Newton forces, and they're in each case, they're separated by what? 3 meters. And so, but they're actually applied at different points on that body. Now, according to the formula for a couple, the couple for all of those should be what? F times D, right? It should be 20 times 3. It should be 60, right? It's just the force times the separation distance between them, right? And it doesn't matter where you apply it. And that's the weird thing about couples is if you apply a couple to a body, the whole body everywhere is sort of feeling this rotational sense. And they call it a free vector because it's not localized. It's just sort of the whole thing is wanting to rotate. It doesn't matter where you look. It's not necessarily about point O, about point A, about anything else. It's all sort of going to be rotating. All experience that desire to rotate. Let's work it out mathematically to show you a little bit more about what I mean by that. So if MO, and we can also just figure the net moment about point O if we want to. And we can also figure the net moment about point A, where A might be right over there. And we could also figure the net moment about point B, which is in the middle there somewhere, right where that other 20-Newton force is, right? You can figure the moment about anywhere, and you're going to find it's the same no matter where you look, right? Whereas if you were just looking at one of those forces, the moment about point O or point B or point A, if there was only one force, it would be different at each of those points. But now that we have that second force, it's going to be the same no matter where you check it. So the moment about O is going to be the sum of m1 about 0.0 plus the sum of the moment of 2 about 0.0, and that's going to equal, well, if we call this F1, it's going to be 20 times 6. Okay, that's going to be minus 120 Newton meters, right? Because this one's going clockwise. You see that? This guy's causing a clockwise sense. But the other force at A, or going up here at the end, is giving us a moment arm of 9, right? 9 times 20 is 180. And it's going the other way, so it's going to be plus 180 Newton meters, right? Oops, there should be a 0 there. So the net, when you add those two together, is going to be 60 Newton meters going counterclockwise, right? Now, what about if you decide to look at point A? What's the moment, the net moment about point A? Now, we're not worrying about an axis at O. What about point A? The moment about point A is going to be also M10 plus M20. We're going to call this, I guess, F. This is sort of 1 of the 2. And what's the moment arm about point A for F1? The moment arm is 3, right? Yeah. The moment arm is 3, so it's going to be 20 times 3. It's going to be 60. And is it positive or negative? The moment of this force about point A, is it positive or negative? It's positive, right? Because the water wheel now stuck at A is because of this force whooshing by is going to spin that way, right? So we have a positive 60. And what's the moment of F2 about point A? It's 0. Why is it 0? Because it's radiating straight out of A, right? The perpendicular distance between this force and A is 0, right? There's no moment arm, right? So it's 0. So the net there is 60 Newton meters going counterclockwise at A as well. Guess what it's going to be at B? It's going to be the same. That's a weird thing, right? So at B, the moment about B is, again, M10 plus M20. That's going to equal, well, F1 about point B, what is that? 0. And F2 about point B is? You said it, right? Not me. 60 Newton meters. Doesn't matter where you look. It's always going to be 60 Newton meters everywhere on that body. Yeah. Yeah, so Dylan's thinking ahead. You could actually make it easier on yourself when you're looking at a couple, is you could just find the moment about a point that's on one of those forces, because that one would go to 0. Then you just have to do one calculation, right? Like, it's easier to do the moment calculation at B and A because there's only one term in the sum, right? Because one of them just goes to 0. One of them doesn't have any moment at all. So that can make it easier when you're doing that. Does it work with 3? Well, couples have to only be 2 forces. If you add a third force, then you just have an unbalanced moment that's just going to be a regular moment about that point. And that will change depending on where that point is, right? The moment arm changes, the moment changes. But when it's a couple, they're the same forces, equal and opposite, but separated by some distance d. It's just that force times d. So you can do the same thing if those forces move somewhere else. You know, same deal, right? You're going to have again, if you're doing it about 0.0, you're going to have a minus 60 Newton meters for F1 and a plus 120 Newton meters for F2. Guess what? That equals 60 Newton meters. Or if they're oriented horizontally, again, you're going to have a 0 because F2 is coming right out of it, plus 60. So that's a weird thing about couples. These? Yes, for MO, it's the sum, well, it's the total distance, right, to the O, right? So the F2 force, you got to go from here to here, which is 6. 6 times 20 is 120. So that's why we call a couple moment a free vector. And you get a new symbol on your diagram. So since it doesn't really matter where you put this thing, what they'll often show is a couple will be indicated by a curlicue and a magnitude on a drawing like this. If you're doing structural engineering, you know, you got to worry about those moments. If there's something applying a moment to it, maybe a cable's pulling this thing up. Like it could be a cable up here kind of yanking this thing up. Maybe it's providing a moment about 0.0, who knows? But that needs to be accounted for, and they will show it often in diagrams like this. Why? Because it's a lot easier, and it happens so often, it's a lot easier than showing it something like this, you know. So you could represent this thing as a curlicue with 60 Newton meters, or you could represent it as a 60 Newton force separated by 1 meter, or you could represent it as a 20 Newton force, you know, separated by 3 meters. What really matters is the net product of the force times the separation distance. And in some, I've seen, like, I don't know if it's a European convention. This is sort of what we're going to get in our textbook all the time, but in some books it might look like, let me draw it like this. It might look something, I've seen something that looks like this. They do it something like this. Like they make like a zigzag, which is sort of, I think, a little less mysterious. People tend to kind of get really kind of puzzled by this when they see that. If you are puzzled, remember you can always replace it with something like this or something like this. If you're ever puzzled by the appearance of a curlicue on your diagram and wondering what that is, you could replace it by an actual force couple that has the same moment as the curlicue. And then everything will just sort of work the same. I say that because later when we're doing structural analysis, you're going to have to deal with these things, and those kind of confuse people until you do it a few times. And you can always replace it with this. So this is the same thing. So here's an example. It's a little weird example. I don't know why. I guess sometimes, you know, some might have happening on it like that. Of course, the important information is, what's the important information here? What's the separation distance between these two, right? But is that easy to find in this case? Yeah. That separation distance is a little hard to find, right? Because it's not, you can't just read it off the diagram, right? It's not 0.2 meters. Something else, right? But we can use the principle of moments to decompose those forces into vertical and horizontal parts and just worry about those. It's a lot easier. So the idea is we can take this force here and represent it by a force that's going, let's call that F1, and a force that's going this way called F2. And we're supposed to find the couple moment. Where should we do that moment about? The origin, or you could do O, or where else could you do it? You could do it here at A. I'm assuming this is coming right at, it seems to be drawn a little bit weirdly to me. Seems like this should be kind of going right here. Well, actually, I guess the 0.2 meters is a little bit in from the end of that teeth, those teeth there. So that's why it's doing it like that. And same one here. So they're basically intersecting at this 0.2 meter point. It's a strange problem, I agree. So let's try it, 3 ways, right? So we can call this F3 and we can call this F4. What is F1? Yeah, 600 cosine 30. F2 is 600 sine 30. Don't worry about those signs yet. F3 is the same deal. It's 600 cosine 30. F4 is the same deal. It's 600 sine of 30. No, right, it's a couple, so it doesn't matter where you decide to do the moments about, right? You could do the moments about point O, you could do the moments about point A here, we'll call point A, right, where this 0.2 meter hits the y-axis, or point B right here. You can pick either of those places. One of them's going to be easier than the other, but it doesn't matter, you'll get the same answer in the end anyway, right? So the moment about point O is going to equal what? Well, what's the moment arm for F1 about point O? Trent, what's the moment arm for F1 about 0.0? 0. Yeah, good. And then it's going to be F2. What's the moment arm for F2? And again, we should be doing this sort of, it's a weird problem. I hate this problem. But it's 0.2, right, away from the origin. So what's the moment arm for F2? Yeah, 0.2. Okay. And we can also add plus, what's the moment arm for F3? 0.2. And by the way, F2, is that positive or negative about 0.0? Sorry? Yeah, you're going to get a negative one there, right? And F3 about 0.0 is going to be positive, right? And then what else are we going to have? We're going to have plus F4 times 0. Good. Okay, well, all right, we found F1 is 600. So basically, it's going to equal, these cancel out, right? It's going to just be, F3, which is 600 cosine of 30, minus F2, which is 600 sine of 30. I'm sorry, F3 times 0.2. Oh, we didn't do the 0.2. Yep, sorry, F3 times 0.2. Sorry about that. Minus F2, 600 sine of 30 times 0.2 as well. That's the moment about 0.0. It's complicated because you have 4 forces you have to sort of think about. Where's an easier place to do the moment that would give us the same answer? B or A? Yeah, A or B would be good, right? Let's try the moment about point A. Moment of all those forces about point A means you can ignore F3 and F4, right? The only thing you got to worry about is F1 times, what's the moment arm of F1 about point A? 0. The moment of F1, this force here, about point A down here. Dylan, I have somebody else. 0 times 0.2. I know it's hard to not. Yeah, it's 0.2, right? And Joel, what's the moment arm of F2 about point A? Oh, no idea. Okay, good. Let's formulate. Remember, this we can travel along this force anywhere, but we got to find what's the closest approach the line of that F2 comes to point A. That's the moment arm. That's this D right here. It's 0.2, right? Okay, Emmanuel, the F1 times 0.2, is that a positive or negative moment? The moment of F1 about point A, should that be considered positive or negative? Yeah, because it's going to make a water wheel at A spin clockwise, right? So we're going to put a plus sign in front of that. And Karen, F2 times 0.2, is that a positive or negative moment about point A? Sorry? Negative, yeah, because it's going to be spinning clockwise, right? So we put a minus there. So it's going to equal F1, which is 600 cosine of 30, times 0.2, minus 600 sine of 30 times 0.2, which is the same as the moment about 0.0. When you have a couple, it doesn't matter where you take the moment. You're going to get the same answer. So why not take the moment at where one of those forces is acting directly, and then you just have to do one calculation of the other force about that point where the other second force is applied. Yeah, that's it. No attention quiz, no nothing. So tomorrow we're going to solve these problems in class, and you will get to like them. Questions? Yep. Mm-hmm.
Are we imagining that are we imagining we're doing this way? And it's going to cause the wheel
So we're thinking about the moment of F2 about point A. And oops, sorry. So if you put a wheel at A, right, F2 flowing downward, going to cause that thing to go clockwise. Is that your question?
Yes. Yeah, yeah.
If your fingers are going that way, yeah, then your thumb is going into the board. That means it's. Mm-hmm. Yep. Mm-hmm. Counterclockwise. F1 about point A is making the wheel want to go this way. Right? You've got a big stream going this way. It's going to make the thing go that way, right? Yeah. Okay. Okay. I didn't even notice. Yeah. It's fine. Yeah, sure. I think I got one. Yep.
The following that was on the quiz and on the test,
Mm-hmm.
it has the two where you